Chapter 6a, Inference for One Proportion. We are going to take the same hypothesis testing structure and confidence interval structure that we applied to quantitative data, where we did inference for means, and construct similar hypotheses and similar confidence intervals for one proportion. Make sure you read through the why and our learning objectives for this activity and also the vocabulary. You can see here in the vocabulary we'll be looking at 90% confidence interval, 95% confidence interval, and the 99% confidence interval. These are the most frequent intervals that are used by statisticians. So in example 1, we're going to calculate a margin of error. So a recent survey of LMC student majors found that psychology was the most popular major. The sample consisted of 326 students, and the sample proportion of students majoring in psychology was p hat equals 0.17. So we use a hat or the caret symbol on top of the p when we're working with sample data. So as soon as you see that p with the hat right here, you know this comes from a sample. So our very first question to think about is this categorical or quantitative data? Well, we know it's categorical data since the response to what's your major is a category and it's not a numerical or quantitative response. So using the sample proportion, we can calculate the standard error, also sometimes called the estimated standard deviation. You'll hear me use those terms interchangeably. And so we use the fact that our p hat is 0.17 and that our sample size was 326 students. So we check the standard error formula. It's the square root of 0.17 times 1 minus 0.17, which will be 0.83 divided by 326. And so from my calculator, you can verify this works out to be 0.0208. And then I'm going to go ahead and also check the conditions to make sure it's appropriate to use a normal model here. Remember doing this back in chapter 4. So we check n times p hat is 55.42, that's above 10, and similarly n times 1 minus p hat, 326 times 0.83 is also going to be above 10. So it's okay to use a normal model. And then we also know from chapters 4 and 5 the z-scores that correspond with the confidence levels 90%, 95%, and 99%. And so when we're talking about the confidence level standard deviation, we put a star on that z. It's just a notation way of writing it. There's nothing that you particularly need to remember, but if you see the z star, remember, oh, that's referring to a specific confidence level. So now we want to calculate the margin of error and confidence interval range for a 90% confidence interval. So remember, the margin of error is the 1.645, the z star for 90%, multiplied by the standard error. So this part here is the margin of error. And then we add and subtract that from 0.17 to get our confidence interval. So our lower bound is 0.1358, or you could say 13.58%. And our upper bound is 0.2042, or you could say 20.42%. And now our interpretation says with 90% confidence in my methods, I predict the proportion of LMC psychology majors is 0.1358 to 0.2042. So remember, two key things when you're writing your interpretation. The first key is that 90% is how confident we are in our calculations or our methods. The second key idea is that our prediction is for all LMC psychology majors, the whole population. We're not just thinking about the people in the sample because we already know that 17% of the people in the sample are psychology majors. So we need to extend our prediction to make sure we're predicting for all psychology majors. So now if we want to construct a 95% confidence interval, we're going to change the value that we're multiplying the standard error by. So instead of using 1.645 for 90%, now we use 2. You could use 1.96 if you want to be a little more precise. And we multiply that by the standard error. So this calculation here is the margin of error. Then we add and subtract that from our sample proportion 0.17. So notice the lower bound is lower and the upper bound is higher because we are more confident. We're 95% confident now in our methods. We need to have a wider range of possible values. So with our interpretation, we say, with 95% confidence in our methods, we predict the percent of LMC psychology majors is 12.84% to 21.16%. So notice earlier I made a proportion in my statement, and now I'm making a percent in my statement. Either way is a reasonable way to express the values in your confidence interval. Here in part E, we're constructing a 99% confidence interval. So notice that the Z star here is now 2.576, and we're going to multiply that by the same standard error, so the standard error doesn't change. And this margin of error now is bigger because as we're going up to 99% confidence, we need a wider interval. So you see we get a lower bound and a higher upper bound because we're more confident in our results, so we need to have more room for possible results. With 99% confidence in our methods, we predict that the percent of LMC psychology majors is 11.64% to 22.36%. Example 2, hypothesis testing for one proportion. So last week, Professor Caldwell told me that she believes that more than 80%, or 0.80 as a proportion, of Umoja scholars see an academic counselor each semester. How can we test this claim to see if it's true? So we set up this study. We want to know, do more than 80% or 0.80 of Umoja scholars see an academic counselor each semester? So remember, the null hypothesis is equality. So with words, I could say the proportion of Umoja scholars who receive academic counseling is equal to 0.80. With symbols, for the null hypothesis, I could say P equals 0.80. So remember, the null hypothesis is always a statement about the parameter, the population value. So we're using P here to indicate the population proportion. And this P that we're using for proportion, it's a different P than the P value that comes out when we're figuring out the normal distribution and the z-score and the corresponding p-value. It's a bit unfortunate that there are two things that use the letter P in statistics. If you're worried about getting confused, one strategy is to always capitalize the other P, the probability part of the normal distribution, and remember the lowercase p is for proportion. The alternative hypothesis says the proportion of Umoja scholars who receive academic counseling is greater than 0.80. Or with symbols, we can say H sub A for the alternative hypothesis is that P is greater than 0.80. So what's the claim? Well, remember the claim is corresponding to the alternative hypothesis. So the claim here is that more than 80% of Umoja scholars see an academic counselor each semester. In the null hypothesis statement, what do we assume to be true about the population? Well, we're assuming the population proportion is 80% of Umoja scholars students seeing a counselor. In the alternative hypothesis statement, how are we comparing the true parameter, that's the value that's unknown to us, to the value that we are assuming is true in the null hypothesis, that's the 0.80. So corresponding with Professor Caldwell's statement, we use the greater than inequality because she believes that more than 80% or 0.80 of Umoja scholars see an academic counselor each semester. So we know from the chapter 5, we saw a similar diagram. So we know hypothesis tests can be one-sided or two-sided. So hypothesis tests for proportions, just like hypothesis tests for means, can be one-sided or two-sided. The difference over here is instead of using mu, now we're saying P is less than some initial value that we choose. This P sub 0 is just standing in for the number that we compare our population value to. So we've got a less than inequality, that's a left-tailed p-value. If we have a greater than inequality, that's a right-tailed p-value. And if we have not equal to inequality, that is a two-tailed p-value because you could have a less than relationship or you could have a greater than relationship for your alternative hypothesis. So let's look at how we write some of these out. So part A says, in a taste test, participants are comparing Pepsi to another cola drink and determining which is sweeter. The scientists planning the study claim that more than 65% of participants rate Pepsi as sweeter. So remember, if somebody's taking this survey, this is not going to be a numerical answer. Last chapter, we looked at someone rating the soda sweetness on a scale of 1 to 10 or 1 to 5. Now we're looking at people answering a categorical question, which is sweeter, and they would say Pepsi or the other drink. So here, we're comparing to 65%, meaning 65% answer that Pepsi is sweeter. So the null hypothesis is that the proportion equals 0.65, and the alternative hypothesis is that the proportion is greater than 0.65. So this would be one-sided, and it would have a right tail because we're on the greater than side of the graph. In part B, a company claims that 80 out of 110 workers report themselves as highly satisfied with their jobs. Consultants have been hired to investigate whether the true ratio of highly satisfied workers is actually different from this ratio of 80 out of 110. So notice I circled the different from. That's telling us right away that our claim or our alternative hypothesis is going to use the not equal to inequality. So the null hypothesis always has equality, so we say the proportion is equal to 80 over 110. And remember, this proportion is our population proportion, the whole parameter value. And then our alternative hypothesis is that the proportion is not equal to 80 over 110. So this is a two-tailed p-value, or we could say it's a two-sided normal distribution, because it could be that people are less satisfied or they could be more satisfied. We won't know until we investigate with a hypothesis. So let's look at setting up a hypothesis test. So take a minute and pause the video to read about this gun violence data from the CDC, the Center for Disease Controls. You can also go check out the website and explore some of the data there. Notice our Pew Research Center poll from 2015 is showing that gun violence overall has declined, and then they separated it out into suicide rates and homicide rates. So you can see the trend is overall declining with maybe some ups and downs more recently. So the Federal Bureau of Justice Statistics, and you can go visit their website, collects and publishes data about crime and the operation of the justice system in the U.S. So using this data, a politician wants to make the argument that the weapons offenses are less than 6% of criminal investigations. So let's investigate if there's good evidence for the politician to make this claim. So we're comparing to 6%. That's the value the politician is using in his argument, his or her argument. So when we write our null hypothesis, remember that always has equality. So the null hypothesis says that the proportion equals 6% or 0.06 as a decimal. The alternative hypothesis, which corresponds with the politician's claim, is that the proportion is less than 0.06. And so this hypothesis is going to have a left-tailed p-value due to the less than inequality. So check the conditions. So we want to check that n times p hat is greater than or equal to 10, and that n times 1 minus p hat is greater than or equal to 10. So we do those calculations right here. So for a random sample, the local police find that 10 of 190 criminal investigations are weapons offenses. So since I see this magic number 10, I know that we are going to be able to use a normal distribution for proportion data. So you could convert it to decimal and then go through the n times p hat calculations or leave it as a fraction. We see what we would expect to see, that yes, n times p hat is 10, and then n times 1 minus p hat is 180, because we know these have to add back up to 190 cases total. And so we say since there were 10 or more investigations in each pile, a normal distribution is appropriate. And when I say pile, I just mean the criminal investigations versus the non-criminal investigations. So remember, we always assume the null hypothesis is true, and we're trying to determine, could the data from the random sample come from the population described by the null hypothesis? So we're going to use StatCrunch. So let's go into StatCrunch, and you can see I put the screenshots here to make it real clear for you to follow along. So we're going to go to the StatCrunch, we're going to choose Stat, and then we're going to go down to Proportion Stats, one sample, with summary, with data would be if we had a whole spreadsheet of data behind us. So a success is just what we're counting. There's nothing actually successful about a gun crime. So that 10 here corresponds with the gun crime or weapons offenses. And then our observations is the total cases they looked at. And the value that we're comparing our hypothesis to is 6%. So remember, StatCrunch is very helpful, and it knows that you need to have the same number in the null and the alternative hypotheses. So as soon as I type the 0.06 in my null hypothesis, it auto fills that in for my alternative hypothesis. And so I just now need to adjust my inequality to be less than. And I like to see the p-value plot, so I'm going to check that. Make sure the hypothesis test bubble is checked. If you wanted to do a confidence interval or check those confidence interval calculations we did back in the earlier question, you could check this bubble here and run it with your confidence interval numbers. So in general, with the one prop summary, the number of successes, you can think about that as the numerator of your fraction, and the number of observations is the denominator. And let's check out our results. So our z-stat is within 1 standard deviation, and our p-value, 0.3344, is above 0.05, our significance level. If we go look at the normal distribution plot, we see we're less than the mean, but we're not more than 2 standard deviations outside of what we expect. And so I recorded those values here and made a note that the p-value is greater than 0.05. So remember that z-stat, or the z-score, is a count of how many standard deviations the statistic is from the center of the distribution. So based on that z-score, which was negative 0.4277, does this statistic seem significantly far from the center? And I say no, the statistic does not seem far from the center of the distribution. The statistic is within 1 standard deviation. This is a typical range. So now we compare our p-value to the 0.05 significance level, and we're in this scenario, in the second bullet, where the p-value is greater than the significance level. So we fail to reject the null hypothesis. There is not enough evidence to support the alternative hypothesis. Notice, we don't get to say the null hypothesis is true. We don't get to say the proportion equals 0.06. We just don't have enough evidence to reject that theory. So this is one way to state our conclusion. As long as you're communicating the right ideas to me, I'm happy with a reasonable explanation, so you don't have to use my exact language. But as a model, here's the language that I used. Since the p-value is greater than 0.05 significance level, we fail to reject the null hypothesis. If the proportion of weapon offenses for all of the U.S. is 0.06 equals 6%, then this would not be surprising to see results like this. Now we can check our calculations by hand. It's not necessary to do this with every calculation, but you might want to practice with the first few calculations. So since we know this 0.06 population proportion, we can actually compute the standard deviation and not the standard error. So we've got 0.06 times 1 minus 0.06, and then we're going to divide that by 190 and take the square root. So you can verify on your calculator. After rounding, you should get 0.0172. And then our p-hat was 10 out of 90, or 0.0526. So if we say p-hat minus p, that's the 0.0526 minus 0.06. That gives us negative 0.0074, and then we divide it by the standard deviation. So we get, after rounding, negative 0.43 standard deviations from the center. So give or take rounding differences, this is a match for our StatCrunch calculation. And then if you want to, you can go back to page 129 and look up what's the probability associated with this z-score, negative 0.43, and you get 0.3336, which is super close to what we got in StatCrunch. StatCrunch results are more accurate, but they're not going to be significantly different, so that's going to change your overall conclusion. All right, so now let's go look at some data from the Bureau of Justice Statistics and see, with all of their data, which is many, many more cases, is there enough evidence to support the politician's argument that weapons offenses are less than 6% of criminal investigations? So, in the most recent data I could find about weapon offenses, from 2013, it showed that there were 10,434 weapons offenses out of a sample of 190,267 criminal investigations in the United States. So since the sample is very large and it represents samples from most communities in the U.S., we are going to assume that the sample has the same properties as a random sample. Sometimes as statisticians, we do this because we can't always get a random sample, but we can get what we call a representative sample. So since this sample is very large and it represents most communities in the US, we're going to treat it as the same properties as a random sample. So our hypotheses don't change. We're still comparing to that 6% that the politicians change. So even though we have more data, we're still asking the same question. So now we want to figure out what is our p hat. So that's the 10,434 out of 190,267, and that is 0.0548. And then our n is a lot bigger. So you can check to make sure that we meet our conditions here for a normal approximation. And of course, since these are very large numbers, we definitely have more than 10 in each of these piles or cases here. So we have lots of data. A normal approximation is appropriate. So now we're going to go into StatCrunch and set up a mathematical model and see how it works out. So I'm going to go again to Stat, Proportion Stats, one sample, and then with summary. And my number of successes, which is the number of weapons offenses, is 10,434. And then the number of observations was 190,267. And then we're comparing to 0.06 proportion, and we're checking to see our weapons offenses less than 0.06, and I'd like to see the p-value plot, so I check the optional graph and compute. And so what has happened here, if you think about our earlier standard error that we calculated, this new standard error is significantly smaller because we're looking at 190,267 cases, not just 190 cases. So we get a very small p-value and our z-stat is very far out. So if you look at our normal distribution, imagine now that the previous data is really compressed because we are sampling from a very large sample. So we get a value way out here. So we record our z-stat and our p-value, and then does this statistic seem significantly far from the center of the distribution? And we say yes, it is -9 standard deviations away. So does the p-value from this hypothesis indicate that the difference between the sample statistic and the parameter value 0.06 is statistically significant? So in this case, our p-value is less than 0.0001. StatCrunch, when it gets super small, will put this notation instead of shifting to scientific notation to indicate real clearly that it's a very small p-value. Since the p-value is less than the significance level 0.05, this indicates statistical significance. So in our conclusion, we can say that we reject the null hypothesis. If the proportion of weapon offenses for all of the US is 0.06 or 6%, we would be extremely surprised to see results like this from a sample size 190,267. We can check our calculations by hand, and you see, oops, I made a mistake in my first calculation, so I crossed it out and wrote in red. So if you're copying my results, make sure you check on your calculator to make sure you get the result I have here in red. And then I rounded my p-hat, and when I subtracted, I got -9.5 here. And then I put a note here, StatCrunch uses the standard error formula, and usually it's pretty close to what we get if we do it by hand. It might be a little bit off, but it doesn't change our final result, right around -9 standard deviations. So why are there different conclusions from when we looked at the local police department data and then now when we look at the data from the Bureau of Justice Statistics? So the difference is that large sample size, the 190,267 cases, shrinks the standard deviation or the standard error, and so comparable results with a larger sample can result in statistical significance. Now, as a statistician, you have to be a little bit careful with this because it can be that you take so big a sample that you're always going to find some sort of statistical difference, even if it's only minute. So sometimes we get a statistical difference, but it's so close that it's not of practicable importance. So you might say here, well, this is only a little bit less than 6%. So you might say it's statistically significantly different, but it's so close to 6%, it might not be of practical importance. It could be to the politician that it is significantly different and they do see it as an improvement. So you want to look case by case when we're saying something is significantly different. Think about, is this a difference that's of practical importance, or could it be it's so close that it's not going to make a practical difference?